So let's look at this design example. So you see this grass lining design? And I think it's the back of this lesson. Thumbs up. All right. So remember, you don't have the numbers there in your workbook, right? It kind of leads you through it, and it shows you the equations, but it doesn't have the numbers worked out. Is that correct? Where can you go to get all that information? You can write it down now as we go through it, but if you don't want to scribble feverishly, if you really want to focus on what I'm saying, this is worked out in HDS 4, and it's actually on, you can have the page number.
I took it out.
It's on, starting on page 5-12 in HDS 4. All the numbers are there. It's the exact same thing that you're doing there in your workbook, but it has the solutions. All right? So don't worry if you miss some of this stuff. HDS 4 has you covered. All right, so let's look at this. Evaluate a grass lining for a roadside channel given the following channel shape, soil conditions, grade, and design. It is expected that the grass lining will be maintained in good condition in the spring and summer months, which are the main storm seasons. So grass linings, we know they're good for filtering pollutants. They can assist with natural infiltration, and that's why we like them, and that's why your permitting agency folks like them. That's why our resource agency folks like them. If you can do it, it's usually the best solution. You use some native vegetation to maintain, right? All right, so what do we have here? We're given a trapezoidal shape, soil, clay sand, and then we're given grass, sod height, and some other stuff. Why do we care what soil we have? Well, we know we have sod though, right? And we're looking to see if the sod remains. So, growing up out in the country, opposed to playing and whatnot, a lot of times after we finished our homework, we had the privilege of doing chores. I tell you what, my folks really instilled a work ethic in me. So chores included weeding the garden. So picture yourself out there weeding the garden. And you know, after a few years, my dad had that garden perfected. And so he would till it, he would incorporate some topsoil into it. You know, it was just fantastic. You just want to pick it up and crumble it in your fingers. The soil's really nice. Weeding the garden, there was a lot of garden. And the weeds, if we didn't attend to them on a regular basis, got really large, but they were easy to pull, right? Because why? It's not necessarily the weed itself, that's partially it, but it's the interaction of the weeds with the soil. Conversely, I have some dandelions and crabgrass and other things growing in my front and backyards, and I don't have a very big front or backyard. So I go out there, and you know how it goes. You see this weed here, and you pull it, and you just pull the top off, and the root is stuck in the soil. It's a clay soil. That weed grips a lot better, and so it takes a lot more pulling, or in the case we're talking about, it takes a lot more shear stress to counter the permissible shear of that vegetation soil interaction.
We will see if the soil or the grass is controlling as far as permissible shear stress. Gotcha.
Well, it's not necessarily one or the other. They kind of act in tandem.
Okay.
So you have components of permissible shear coming from both the vegetation and the soil that it's rooted in. So it's kind of like a combo effect, if you will. So that's why we need to consider both vegetation and soil, and that's why these types of examples get a little bit more complex. So again, we have to find out, we need the applied shear stress, and so to get the applied shear stress, we need a flow depth, right? Because we said gamma d times the slope, so we need to find the flow depth. We're using Manning's equation, so we have to calculate, our area, our wetted perimeter, and we have to go through the shear stress calculation, and we see that it's an iterative process. Okay. So we initially do a guess, The other thing that makes this complicated is we need a roughness, a Manning's end. And we're dealing with open channel flow, shallower flow, larger roughness elements, so we're considering relative roughness. So our roughness is dependent upon the depth that we initially guess at. Okay? We just don't go to a table and just pick out a roughness and that's exactly what it is. It's a function of our flow depth. And so this is where we get into this iterative procedure. All right, so again, walking through this example that's in HDS4, we see that relative roughness for this vegetation comes from this equation. This alpha parameter, that's a conversion. The C sub n, and that comes from what types of vegetation we have. You know what's the stiffness of it, what is its stem system like, and we just looked this up in the table. And it's also dependent on shear stress, because we need to know whether that vegetation is upright or lying down. If it's lying down, its roughness will be less. If it's standing up, its roughness will be more. So again, digging into the minutia, but the basic concepts are pretty easy to understand it there. Here we're using average boundary shear stress to calculate Manning's roughness. Don't let that throw you, because when we're looking at the applied shear, we're still using the water depth, not the average boundary shear. Okay, but in this, just to calculate Manning's end here, we're using the average boundary shear stress. Then after we figure all that stuff out from our good friend, assistance from our good friend Heck 15, and looking up these couple of parameters based on what type of vegetation we have, we actually calculate a roughness coefficient, 0.028, which sounds fairly reasonable for some light vegetation. And then we go through and calculate our Q that we had to guess at because we guessed it a flow depth, and we come up with 41.2 cubic feet per second. So this was based on our guess of water depth, and we actually need to compare that with the design flow. And we see that it's, I don't remember what our design flow was. Could you say that a little louder? 17. 17. So we see that what we guessed at is way too large, and so we have to iterate again. So we have to choose a new flow depth, and it gives us an equation to try to hone in on the answer more quickly. We choose a new flow depth, we calculate new area, wetted perimeter, therefore hydraulic radius, and then generate a new Manning's roughness. And so you can see where this could take a few iterations until finally, I think it's after the third iteration? Yeah, after the third iteration, we finally guess it right. We calculate or guess a flow depth, and we went through the calculation and then calculated our flow rate from Manning's equation, and our guess comes within 5% of the actual, and we say we're good to go. So we had to go through all of that to make sure we had the right flow depth, then to calculate our maximum or our applied shear stress, Cal sub D. All right, so all of that work that you see there in your problem, and again, that's replicated in HDS4, is so that we can just figure out what our applied shear stress is. The water, the design discharge is applying the shear stress to our channel. All right, you can calculate the applied shear, and it's 1.29 pounds per square foot. Let's take a pause there, and do you have questions? So if you missed any of these numbers, again, don't get concerned. HDS4 has the same numbers that this is actually HDS4, so this is all written out in there, and you can go back and revisit that and fill in your numbers if you want. As an aside, so I also have a master's degree in counseling, so engineers and designers and folks that are fixated on the minutiae and the fine detail tend to have obsessive compulsive features, and that's not a bad thing. There are people in the world that need to pay fine attention to details. Think if you had a surgeon, you're going in for major surgery, and the surgeon did not care about the fine details. I would not feel very safe going into that operating room, right? There are people that need to do that, and we tend to focus on the minutiae and the details. And then if we can't pay attention to the details and make sure we have closure on things and everything's the way it should be, maybe that throws us for a loop a little bit. And that's quite all right. So what I'm saying is, don't worry if you did capture everything. This again is in HDS form. So we figured out our applied shear, 1.29 pounds per square foot. We have to figure out what our combination of our vegetation and the soil it's in can resist, and then we make sure that it's more than 1.29 pounds per square foot. And if so, happy hour. If not, stay thirsty, my friends. Okay, so the permissible soil shear. So we have to figure out the components of the permissible for both our vegetation and our soil. I just want to make sure I haven't skipped over any steps here. Okay, good. So it's first going to look at the permissible soil shear stress. We have kind of like a cohesive or a sticky soil. And those are clays and silts and all the very fine-grained soils. So one of the key pieces of information we need, the plasticity index. And since this is a sandy clay, we also need to look for our void ratio, which was given, and that's this lowercase e. That void ratio is 0.5. So with that, and these values that we can look up, to get a better handle on the exact type of soil we have and the shear stress it can resist. We have all these coefficients, and you go to the cohesive soil table in HEC 15, and it tells you, based on the plasticity index, what these coefficients should be. And it's basically just you plugging them in from the table and coming up with the soil resistance, the permissible soil resistance of the clay, 0.068 pounds per square feet. So that's part one. We have a hybrid system. We also have the vegetative component that we need to also address. So going back to HEC 15, we see that the permissible shear stress then of the vegetation depends on the soil components, and then these other values that we look up that are dependent on the type of vegetation we have, how good a condition it's in, what its density is, what its stem height is. So all of that information, again, is not something you need to know, it's not something you memorize. It's tabular values that you pull out of HEC 15 or another type of resource document. So you do a plug and chug, you plug all this stuff in, and then you get the final permissible shear stress for your vegetation in this specific clayey, sandy soil, and it comes out to be 2.7 pounds per square foot. Okay, so that's the permissible. So what is your verdict after doing this 2-hour calculation? The permissible is 2.7 pounds per square foot. The applied is 1.29 pounds per square foot.
Good.
Lining is acceptable. The applied is less than what the lining can tolerate. And the lining, again, is the vegetation in that sandy clay soil. So given we're not mentioning safety factors here, that certainly comes into play, but just on the analysis itself without a safety factor or safety factor 1, you can say, I feel good about this lining for my 10-year event or whatever it is, whatever return period you have. However, is that actually true? I'm going to throw a wrench in the works, because this is something that we don't consider all the time, but it's very critical. 1.29 pounds per square foot is the applied shear stress, right? What was the permissible for the soil? .068. Is our vegetation going to grow right away?
No.
No. Unless you, I mean, if you were to put down sod mats or something like that, sure, right? But how often do we do that? It's usually hydro-seeded, right, with some mulch and maybe a little protective coating of some kind. And we hope that in a growing season or two, it's really well established and that our design flow does not occur within that first year or two until our vegetation's established and we're good to go, right? Well, this comes into then the realm of, do we need some temporary erosion control until our vegetative lining is established? And then if we do a biodegradable temporary erosion control matting or some kind, we can see that matting and we check to make sure the permissible shear stress of the temporary erosion control is able to resist something that's maybe not necessarily the 10-year flood, but at least something fairly substantial. And that gives us a better chance for success. So the same kind of idea applies also with stream restoration projects, because we see these all the time. We put in this nice new sinuous channel and we do some vegetative planting here or there. That planting and that natural protection maybe is not well established for several growing seasons. And if we have our flood occur within that time frame, we have to go back in and typically fix it, revegetate it, maybe have to do something with riprap or some emergency repairs. So just a caution, things seem straightforward until they're not. So we have to consider the what ifs too. That seems like a lot of work to do by hand. I don't know about you, but I wouldn't want to do many of those vegetative lines by hand. Well, here's the good news. You don't have to. Unless your supervisor's making you prove that you can actually do it for whatever reason. Maybe they're a sadist. I don't know what the deal is. I don't want to criticize your supervisors.